That one put a smile on my face, Justin. That was funny, man. How's it going, Toby? How's it going, Justin? Hey, what do I do here? Okay. Bam, bam, bam. All right, let's keep the grind going. The grind keeps going and going and going. Oh, Don recommended my stream. I was literally just on Don's stream actually. I was gonna, I was watching him go through that flux exercise. Actually, I just had a little calculation from it. But hope you're having a good day. Thank you. I am. Yeah, with Don streams, when Dom's doing his his magnetic stuff, I always debate whether I should chime in or not. But I feel like it's just better that they work it through. And they also have chat engagement too, so it's pretty cool. Nothing better than everyone working on the same problem. 2.37, 2.38. I'm going through measure theory myself. Any tips? Oh, nice. Well, first thing I should ask is what book you're using. Because that would that'd probably give me an idea of what tips I can give you. Okay. How do I restate this? Are you using Royden? Are you using Rudin? Are you using what's the other guy? There's another book out there. Oh, I'm just starting. I'm completing measures and functions. I see. Any tips? So the thing that I've noticed when I go through this, when I go through measure theory, is that it relies a lot on supremum properties or infimum properties. It relies specifically on this one right here. Let me show you which one. Okay, I'm far from this page. It relies. So I don't know if you can see the problem in the bottom, the ones with the stars. If y is an infimum of the set S, then for each epsilon greater than 0, there exists an A and S such that this inequality holds. This is used a lot, like This is used a lot in measure theory. Like this is probably used like the most so far out of all of the undergrad real. Um, yeah, so this is very important. I do struggle at proofs where proving something is always a headache. Yeah, and unfortunately measure theory is just all about proving things. Proving things about measurable sets, measurable functions. But this shows up a lot. Like I could probably even pull up a random page on my notes and show that it's there. Let's see. By the infimum, I need to. If I say by the infimum property, anywhere I say by the infimum property, I'm basically referring to that property. Oh, not this one. But it's a lot of set theory. Like there's a lot of set theory that you kind of have to also know. Um, let's see. I think my first page for sure has it. I know it's somewhere in in that set of notes that I have, but I think here I actually explicitly say that I'm using that property. Yeah, it's right here. See, I even have it like right here written, but it's like it shows up all the time. Like this is like not the only time it shows up in these notes. So you can see I'm literally that's literally the property that's on that in that book. Can I share something with you? An exercise, it's simple, but I would like to know the uses and applications of it. You could. I don't know if I'll be that useful. I'm still kind of like, I wouldn't say I'm the expert, you know, but you can for sure. Like going through measure theory is like basically, um, if you're going through a book, it's basically kind of like trying to fill in the blanks or the details that like set theory details or undergrad real details. That's basically like the whole thing about measure theory. Hmm. I don't know if you're gonna link it or if you're gonna if you're going to like if you're typing it out. Da-na-na. Wonder what would happen if I do this. Oh man, that's not good. I'm looking for English version. Oh, no worries, no worries. Yeah, just let me know. I'll be working on this real quick. Wait, I think I like this one better. Okay, it's a Google Drive link. Let's see. Oh, I see. You got to measure space. And you got two sets in F, which is the sigma algebra, it looks like. And you want to show that A is the measure of A is equal to the measure of A minus B plus the measure of A intersect B. And if they are subsets, that the measure of A is less than it. Okay, okay. Okay. Yeah, yeah, yeah. What is this? What language is this? Curious. The nice thing about math is like even if it's in a different language, if you like know the the theory, then you can kind of get a lot of the information from just like the notation. Damn, these are exercises? Holy moly. They're not terrible, but like this is very interesting. Oh, French. Yeah, French. Yeah, it's a universal language. The mathematics. That's one of the things that if you know just a little bit of a different language, you can usually study math in that language, which is kind of cool. So what was this? What was it about this problem that you were like thinking about? Not the button mash. That emote's so good. How you doing, Joseph? The first one? Okay. So it's basically measure the measure a Lebesgue, yeah. Not that look. Hey, Lebesgue, once you get past the grind of outer measure, Lebesgue stuff gets like super nice. All the dirty work is done in outer measure. You use the first one to prove the fourth? Let's see, what was the fourth one? Yeah, you use Um, okay, so you basically use this to prove this. And so are you just wondering, are you wondering how this is done? Is that what you're wondering? I'm here to learn about properties of LeBron LeBron measures. Leave it to Mac to come up with some fucking witty phrase or something. Okay. Yeah, this one shouldn't be too bad. So I think the first thing you should notice is that for a set A and B, we're going to use a picture, but you can also do this using set theory. Um, you can do this using set theory because it's like if you rigorously want to do it using set theory. If you have a set A and a set B, yeah, you just rewrite it as a union, right? So if you just have to basically know that this is A minus B, and this is A intersect B, and so A is just the union of those two. Right. So it's A is a union of A intersect B. I mean A set difference B union A intersect B, and those two sets are they're disjoint. And think from these two, it follows that you get the equality of the sum. Yeah. It's basically it depends on them being disjoint. Otherwise, if they're not disjoint, then you don't get the equality. I definitely understood everything you said, even when De Morgan is trying to look me from the grave. Tell De Morgan, no means no. Oh. Yeah. No problem, no problem. A good exercise. A good exercise. I was wondering, like, this stuff right here is like, it should be an exercise. Yeah. Cool. I'm actually curious what book this is. I don't have my homework. I'll be dropping. Okay, I'll do my best. I mean, I'm basically streaming me like going through like the details of measure theory. So um, I'm not trying to say stick around, but like maybe if you stick around, you can kind of get some like intuition or see what things I'm using over and over again, and maybe that might help you. But I've told you what shows up a lot. Um, specifically when you're doing these big theorems, but when you're doing like the exercises, a lot of it hinges on like set theory stuff. Okay, what was I gonna do here? Okay. So I'm assuming mu is measure for you. It's not outer measure, right? It's not outer measure. It's the Lebesgue measure. It's crazy how like half of the stuff you're doing is literally taught in my proofs class. Well, not really taught. Wait, no one's teaching it? You're just learning it on your own? Yeah, this stuff, like the stuff that I'm doing in measure theory is like I can't stress enough how much undergrad analysis, like how valuable that is. Like if your undergrad analysis is like solid, then measure theory, it's not just undergrad analysis. What am I saying? It's undergrad analysis and set theory. If those two are good, then this should be okay for the most part. There are some really challenging problems, but like a lot of it is doable. Yeah, it's measured, but not Lebesgue. We didn't know that. Oh yeah. Yeah, that's I remember. Yeah. Yeah, it's a measure. It's like the general notion for measure, right? And then Lebesgue measure is kind of like one of those examples. But it has those. It's basically the section I'm working through, but they're specifically focusing on Lebesgue measure. So you're already going through measure. There's another book that's very similar to um, the notation you use. This is the book that I used when I first learned measure theory. When I took this class. It's this book. So it goes through outer measure, defines it using these like absolute values, like notation. Um, builds the properties of outer measure, a few properties, and then it talks about what we want for measurable spaces. Like these are the 4 things we want for measurable spaces, and then kind of like what we can't have. Then sigma algebras, and then some stuff about measurable functions. And then finally, it goes through measures. So this is the notation is literally what you used. I have so many books I need to read. I don't even have time to read Axler. Yeah, this don't. If you don't have time, you should definitely not read something you don't have time for. But you know what, Axler, you should make an exception. Even if you don't have time, read it. The whole class subject is measure and integration. Is it a book? Yeah, this is a book that's free. It's Axler. It's Axler's book on measure theory and analysis. So you can see this is the same notation you're using. It also uses lambda, or I guess al, as Lebesgue measure. But this is the, let's see. Um, it is this one. It's this book. Oh, I shouldn't even link this. I should not link this. This, if you want to buy the book, it's here, or you can go on the Springer website. You can probably buy it for cheaper there. But if you just want it for free, you just Google Axler, and he has a website called Sheldon Axler's website. Let me just link it in the chat. And this website, you'll basically find all of the books that he's associated to. Either he's like solely published it, or he's a co-author. It's the second book in this website. And the nice thing about this is that he keeps track of some of the typos and stuff like that. It's in the errata. Yeah, there you go. Teaching fellow is even asking us to read Tao, both analysis and topology, like as if we actually have the time. That's funny. Yeah, I think as an educator, you just like assume that your students have all the time in the world. Yeah, of course, of course. It's a good book. This book, the book that I use is really good. It's like a gentler. It's like a gentle introduction to measure theory, which is why I think it's really good. The book that I'm working through right now is a more um, comprehensive look at measure theory. They're still kind of, it's still the same, but here's like the main difference. I'm gonna show you the main difference that I've noticed. One of the main differences is right here. In Axler's book, he defines a measurable set as a set in the sigma algebra. Okay, this is done in Axler's book. In Royden doesn't do this. Royden defines a measurable set using this definition. If a set is measurable, if it satisfies this equality for all sets A. And when you start here, you can actually build measurable sets and show that they form a sigma algebra. So Axler doesn't even do this in his book. And so like it's kind of like he's kind of taking some of like the key points and summarizing it into a definition. And in some cases, when you're first learning a subject, that's better. But if you really want to understand like the details, it's good to go through this stuff too. And it's cool. Like this is a lot of good. It's like a lot of good practice for undergrad real and topology and set theory. A lot of set theory. A lot. That's why all I'm doing right now. That's why all I'm doing right now is doing my best to get at least an A minus. Then I'll just cram everything during the winter sesh before spring semester starts. You know, Tao's book is actually really good. The analysis book. I actually never really looked at Tao's books until recently. But when I looked at his analysis book, it's like fantastic. I think it's better than Rudin in my opinion. Like Tao goes through the construction of the real numbers and like detail. And he'll even explain some of like the nuances, like why there are certain things happening. He'll explain if he's being like if he's not being rigorous, like if it's just informal. And when he does that, you kind of think, why is he doing that? It's probably because it's very difficult to formalize it. But he actually builds the real lines. The Rudin also does that too, but he starts at the rational numbers, or he builds the rational numbers first. All of them are in French. Yeah, definitely. If you have them, I would be interested in looking. I just like to see kind of the general flow of like the theory. That makes sense. Even though I can't read it, I can at least make out like some of like the flow of the theory, and then maybe like the flow of the theory kind of gives me insights into how other people like approach the subject. Okay. So last time I was actually going to do, I stopped here. Where did I stop? Actually, I didn't even stop here. I stopped. Every interval is measurable. Did I stop here? Yeah, I stopped at every interval is measurable. This actually was a pain, so I'm kind of glad I didn't do it on stream. I mean, I could have done it on stream, but it would have taken me a while. But there was like a lot of details that was not shown in the proof. Like basically all of this is not shown in the proof. So I'm glad I did that off stream. This one was interesting. Oh, interesting. Symmetric difference. I literally went through this just a while, like a day ago or two. Or I used this. That's funny. Got limb soups in here. Good. Wow. I got Borel stuff. Interesting. I mean, if you're working through function stuff right now, I will be working through it pretty soon. Measures. Okay, that's good stuff. Good, good. Interesting. I read Alcock's book, How to Think About Analysis. I don't think I have. Let's see. How to think about analysis. I think about analysis. Interesting. Only $28. I hate that it has two names. By the way, this makes me so mad. Advanced calculus or real analysis. That has caused so much confusion for me. How many pages is this? 272. Holy moly. Considering a math major, this book is an excellent intro to analysis. How to study as a math major. Interesting. Interesting. Oh, I can't look inside the book. Subject in most undergrad mathematics degrees is elegant, clever, and rewarding to learn, but it is hard. Even the best students find it challenging, and those who are unprepared often find it incomprehensible at first. This book aims to ensure that no student need be unprepared. It is not like other analysis books. It is not a textbook containing standard content. Rather, it is designed to be read before arriving at university and or before starting an analysis course. Interesting. Or as a companion text, provides a friendly and readable introduction to the subject by building on the student's existing understanding of 6 key properties: sequences, series, continuity, differentiability, integrability, and the real numbers. So analysis, real analysis. It explains how mathematicians develop and use sophisticated formal versions of these ideas. Oh, that's cool. Provides a detailed introduction to the central definitions, theorems, and proofs, pointing out typical areas of difficulty and confusion and learning how to overcome these. Oh, this is cool. It's cool to have a book like this around. I'm gonna buy this eventually then. Oh, not this guy. I've also seen this book around. Bartle. I've heard Bartle's good. Let's see how much this book is. Hardcover, $209. $209. Hashtag not worth. What's not worth? Play Machamp? Yeah, but Play Machamp is not worth. Yeah, I 100% agree. Math with Professor V carried me through analysis, aka calculus. Who's Professor V? Oh, 120% not worth? Don't you know it got buffed? It's better now. Is that a YouTube series? Or is that a book? I feel like it's a. Oh, interesting. Yeah, I suspected it was a channel. Dench. Yeah, yeah. Yeah, it's always good to find good YouTube channels that do math. And there's not a lot of them, to be honest. If you ever have secret math mediums, call them run the boost. Machamp got buffed. I'm probably gonna play Machamp today. Now that you mention it, I think it works well in some cases. Specifically, um, specifically, submission. Yeah, Baby Rune is not a good book. Good first. It's not a good as a first book. It's a good like if you want to read through it again. But a good first book is the basically the book I showed you is a good first book. The what was it? This book right here. This book is a good first book. It like it boxes everything. It boxes all the key results. And in the first few pages, it even has like all the big theorems. A good strategy that every person taking like a math class should be doing. They should be like keeping track of all the big theorems they proved. To be fair, you can still do stuff with it. It's just much harder now. I found it easier. Honestly, using the Machamp alt is much easier. So they made Machamp alt easier to use, but obviously, like you mentioned before, like there's a lot more you can do with the Machamp alt if you have like the flexibility of using the second stage. But I think the obviously I think the reason they changed it was because to make it easier for for people to use. What does that mean anyway? It means that your alt doesn't miss, at least the barrage part. Because I think when people are in the first stage, people like kind of walk around and tend to miss their ult, either because of, like they get nervous or something. I'll cram that during Thanksgiving. But the the um the Tau book is also really good. The Tau book is really good. I haven't read through it, but like from what I skimmed so far, is like it is like it is comparable to this. This doesn't build a real line. Tao's book does, and it actually has a lot of details of what he's doing. So I might even recommend that book even more than this one. Yeah, if you think about it, Pacho, from the perspective of how a lot of Unite players play, they kind of just like they don't really use their ult effectively. They'll like they'll use it in those cases where like they how can I explain this? Or they'll use it inefficiently where they ult somebody just because they're next to them. They like play like bots basically. And so in situations like that, it's just easier. Like it's just like having the ult come out immediately is just like better for those kind of players. They're not going to be doing they're not going to like strategically use it to like neutralize um, some sort of like damage or CC or it literally just double tap. Yeah. But I don't think they even think about double tapping. They just tap it once, even though you can do that. It's the problem of the Unite player mind. Tao's good. Tao's great. Tao's I was skeptical about Tao because he's like one of those really smart guys and usually like that everyone really likes and usually people like that I feel like they don't write well, but when I actually looked at his book it was really well written. Like he writes it for the student, it looks like. Oh, the is that really how it worked? That would honestly make sense in the Chinese version. Oh my. I don't know. Honestly, I don't know a lot about the Chinese version. I know that I think you could walk around, but I don't keep track of that stuff. Which game? It's Pokemon Unite. I will be switching. I most likely will be switching over to that after I do this theorem that I'm working on. that I'm working on. that I'm supposed to be working on. Um, are you Chinese or where are you from? I'm from Texas. I'm not Chinese. Oh, I'm not the freaking forest fired guy. Only you. Does anyone even remember this guy? What do they call him? Something Smoky. Smoky. I was about to call him Yogi the Bear. That's another bear. That's Smokey the Bear. Man. Holy moly. Yeah, yeah. I'm not Chinese. If you really want to know, I'm actually part Mexican. I don't know what the other part is. There's no documentation. My team needs one more point to win this round of Battle Frontier. The hell's Battle Frontier? Bro, denying his whiteness? It could be white. I wouldn't doubt it. Everyone thinks I'm white. People either mistake me for being a white person or um or someone. What was the other demographic? You don't play Pokemon? No, I don't play Pokemon Go. If I played Pokemon Go, I would literally chat more when you play Pokemon Go. I only meme. I meme when you play Pokemon Go. The heck? Meme Lord. Yeah. I mean, I've effectively learned a lot of the Pokemon Go stuff watching your stream. When I watch your stream, I kind of know roughly like how the gameplay works, but I've never really like played it myself. Why did I pin that? My mouse is hovering the text, and I clicked and it pinned. Albanian? No, I think Armenian is another Armenian. Armenian is another one. Um, something else. Ryan don't even like Pokemon. He only plays Unite for the great gaming experience. Exactly, Mock understands. You know, Mock, the me deciding I didn't like Pokemon was actually post me playing Unite. And so the reason why I play Unite is because I played it so long that I've invested into it and I know roughly how to play it. Um, and so now I'm like stuck playing the game. But me liking Pokemon, like it's degraded over the time that I've been playing the game. And it's not because of Pokemon Unite, by the way. It's literally not because of that. It's partly because of that. So have you learned the most important lesson? Maybe I've learned some lessons. I don't know, man. You tend to mess up a lot, it seems. Or you never could have won the battle. That's those are the two things I hear from you when you're playing. Should I bait? Let's all play the card game. It launches on the 30th or so. What card game? Some battles come down to 50-50. That's fine to lose though. I thought it already came out. Isn't that what Spraggles has been playing this whole time? Yeah, isn't it already out? Or is that some sort of like beta version? Oh, interesting. I see. I might be down to play. I always say that I do like the Pokemon cards. Like, out of all the Pokemon games out there, I think Pokemon TCG is the most interesting. I also like the artwork. But yeah, I would probably be down to play that game actually. Alright, I need to get through this really fast. Yeah, of course, Toby. Thanks for dropping by. I hope whenever you ask questions I can help. Measure a partition of E. Okay, proposition 12. What was this one? 13. Union of countable collection of measurable sets is measurable. Oh, what the heck, man? Brother. What happened here? What's this? What the heck happened here? Ah, I'm not gonna think about it right now. I think it's literally the proposition 12 too. Holy shit. Yeah, it is this one. 2.22. Okay. Hate when this happens to my notes. Fix this. Okay. Proposition 5. That's one of the earliest ones. It's this one. This is here. Subadditive. That's this one. 2.8. 2.8. Okay. Okay. Finite additivity. It's here. It's right here. Disjoint measurable sets. Yeah, measure partition is disjoint, I think. Where is it at? Or I think I already defined it somewhere. Yeah, measure partition is disjoint. So that's corollary. That's going to be corollary 2.2.141. How do you do stuff every day without burning out? I tried only doing. I also don't do stuff every day. Sometimes I just don't study for a day. It depends on how I feel. Um, but I typically try to do like 2 hours at least. And sometimes that will like that leads into like larger study times if I'm feeling it. I'm feeling it. And sometimes I just don't feel it, so I just don't do it. So you kind of have to like kind of keep it in mind, to like if you're not feeling it, take the day off, but like don't take too many days off. Maybe like a good safe place to start is take one day off and see how that works for you. And if the following weeks, like if you feel like there are like no immediate um, deadlines, then you can take more than one day, or you can take 2 days or 3 days off. Sometimes you just need 3 days off, like to kind of like recharge, and then you can kind of grind again. But it also helps that I like doing it. I like going through this stuff. It's super interesting. 2.14.1. I will admit that going through older theory that I already learned is a lot harder for me to do because it's very um, it's I guess boring in a sense. Like I'm trying to think of like an equivalent example. It's kind of like, and maybe you've seen this from like your peers or from other people that like other people's stories. It's kind of like when you're learning calculus, um, and you struggle with calculus, and the reason you're struggling is because of the algebra. It's kind of like getting motivated to relearn algebra. There's like a lot of stuff that you already know. Well, it's stuff that you already learned, but like it's not very like interesting to learn again. That's kind of how I feel when I try to learn or like relearn older stuff. So if I were to do this for like, if I were to relearn proofs, that would be hard. That would be hard for me. And at some point, I am going to do that because I do want to make like um, a playlist of videos, but that requires me to kind of like look at proofs and how it's taught from different perspectives, and then trying to nitpick all the things that I like. This is result 2.4, I think. I use this result so many times. I think it's 2.4. Yep, 2.4. So if you're doing this so often, you start noticing what results you use so often. 2.4 I use almost all the time. 2.4. The measure. Wait a minute. This is N. And this is equal to the sum. Okay. This is for all N. Yeah. The left-hand side is independent of N. Consequently, see this part right here? This part right here is missing details. So if you've taken analysis and you read basically this step from this step with the inequality to this step here, it should kind of like ring there are missing steps, and it's missing like undergrad analysis steps. So what are those steps? Well, let's fill in the blanks. Okay. So we have N EK is less than or equal to the measure of this. So there's going to be two cases, I think. So case one. Case one is that this measure is infinite. Suppose this is infinite. If this is infinite, then the sequence of partial sums can either be finite or infinite, and since it's positive, since the terms in the sum are the terms of the sequence of the partial sums are strictly positive, it can only be positive infinity. So this is always true. Since m this is greater than or equal to 0 for all k, then this is positive. And so this measure, so the sequence of partial sums, the limit of the sequence of partial sums is either going to be it's bounded between 0 and infinity. So if this is infinity, then this was also this inequality is always going to be true because this is either going to be finite or infinity. The only issue we would have had is if this was negative infinity, but that's not possible. And then case 2 is this is finite. That's less than infinity. Have you read Principia Mathematica? I have not actually. Honestly, that book is incredibly hard to read. Anytime you try to read a book that was like it was a banger in 1910, anytime you try to read an old book, it would be so hard to read because like the notations are different, the language is different, like it's so difficult to read old books. I've tried. I've actually tried reading Principia actually, but it's very difficult. You just know they spent 300 pages trying to prove 1 plus 1 is equal to 2. I remember learning about Lebesgue measure in uni. Nice. Wait, undergrad or graduate? You know, Mac, there are. I've heard that there is a way for the computer to prove that, and it takes like thousands of pages. Like the computer will prove it in thousands of pages or something like that. It's something I heard a while back. undergrad, we spent way too much time on it. So your class is obviously an analysis course. Was it like, did you start from sequences and series, and then you worked your way up to Riemann integration, and then you studied Lebesgue, or was it like you did that first sequence and then you took a second sequence on measure theory? Unless there's a different route that I'm not aware of, because it's sometimes people do spend time on Lebesgue stuff at the end of of an analysis course, like an introductory analysis course. Lebesgue strangely was in a functional analysis class. A large part of it was measure theory. Ah, yeah. Measure functional analysis is reliant on Lebesgue stuff. It was a third year. Oh, okay. Yeah, it's functional analysis is like very topological heavy, but it's like also dependent on like on measure theory and some of its consequences. But yeah, when I took functional analysis, it was um like I have already taken Lebesgue stuff, like I've learned about it, and so like my class worked under the assumption that you already knew Lebesgue. Am I a grad student? I'm a grad student right now. Wait, you did it in undergrad? You're learning functional analysis in undergrad? That's insane. I just realized that. That's insane. That class is not easy. Okay, this case is actually not that bad. This actually requires undergrad analysis facts. First, it should be it's clear that this sequence of partial sums, since it's positive, um, since the sums are positive, it's an increasing sequence. I took that class and got an A just to be very mediocre data scientist. Oh, that's feels bad moment. So you studied data scientist? That's a statistics based um okay, so that's a statistics based major, isn't it? Applied math, yeah. You should be learning mediocre data scientist still makes bank. I don't want to distract you, sorry. No worries. Honestly, when I'm working through this stuff, if you guys are like if you want to chat, like I'm more than happy to chat. This stuff is not like it's not stuff that I need to do. Like I'm working through this for fun. I've already learned this stuff. I'm kind of going through it again to be proficient at it. But like I'm streaming it. So if you guys ever want to chat about this stuff or just want to chat in general, like that's what this is for. Is the null set the same as zero? The classic question. I really like your lecture notes. Thank you. I'm doing it in a way that if I were to never look at this again, that I can read it and pick it up again. It's not polished, but basically my stuff is like filling in every single detail in the book that I'm looking at, which is to the left, which is Royden. And so I'm filling in the details between this two steps right here, which is a undergrad analysis exercise. No, Mark, the null set is not the same as zero. It is not. But I think I heard that you can define it using zero somehow. No, not using zero. Maybe I'm mixing it up. I had to rethink about that. But no, the null set and 0 are not the same. Okay, so since m e of k is okay, so one thing I should note that this okay, I can do this. I can do it. I want to try to make sure that the logic flows nicely. So since e sub k is a subset of u e sub k, then the measure of e sub k is less than or equal to um, the measure of the union e sub k, which is less than infinity. And so, and that was by result. That's by result 2.4. So the measure of e sub k is bounded between infinity and 0, but not containing infinity. Hence, the sequence of partial sums which is this sequence, is increasing. Got me thinking why data scientist is taking functional analysis. Functional analysis goes over Hilbert spaces. Are there applications of Hilbert spaces in data science? There probably is. There are applications everywhere for Hilbert spaces. Is increasing. Yeah. Furthermore, um, the sequence of partial sums is bounded. Is bounded, and it's bounded above specifically. It's bounded above by the measure of the union. Oh no, not bounded by the measure of the union. It's bounded above by, where is it at? Yeah, by the measure of the union. Thus, this is where undergrad real comes in. Thus, by the bounded monotone convergence theorem. Almost all alumni become data scientists, but all were required to take these theory classes, and we don't even have an actual data science course. Oh no. Interesting. Interesting. That's an interesting situation. So it's like all theoretical stuff, but you don't really get to like apply it. That's kind of insane, actually. Yeah, that's by the bounded monotone convergence theorem. This sequence converges. This converges. This is less than, and it converges. Oh no. It's less than infinity. Okay, that's part of the argument, and I think the other part is that we have to use the limit properties. So the first thing we had to show was that this sum doesn't just go to infinity for some reason, and that's what we just showed. If we take the limit, or if the sequence, we needed to show that the sequence of partial sums doesn't just blow up for some reason, and that's done through bounded monotone convergence theorem. And then there is another result in real analysis that says that okay, since this is less than or equal to this, since this is less than equal to this, and I'm trying to remember what property of sequences this is. Let's see. When you finished with case 2, can you please go over this theorem? Yeah, of course. Let's see. See, where is this? Subsequences. Sequences. Algebra of limits. Wait, I'm on chapter 2. No wonder this doesn't look familiar. Cauchy. Okay, it's got to be here somewhere. Squeeze theorem. Okay, yada yada. I know it's a sequence property. Where is it at? It should be in this section. Is it this? Yes. This is exactly what I'm using right here. The order properties of the sequential limits. Yeah. So suppose A and B are real numbers and Xn is a convergent sequence of real numbers. So it depends on the sequence being convergent, which I just established. If the sequence is less than or equal to some B for every index, then the limit is less than or equal to B. That's what I'm applying here. Then this is less than or equal to this. And this is by order properties of limits. Okay. And that basically finishes the proof. Right? Because we established inequality in both directions. So go over this theorem. This theorem is basically saying that if my sets are measurable, like An easy, tangible example is like the intervals. Like if I have these measurable sets, they're disjoint. A, B, C, D, this is E, F. If they're disjoint and measurable, in this case, intervals are. So this is like a nice example to use for this. It's saying that if I take the union of these, and so I'll call this I1, interval 2, interval 3, interval 4. So what it's saying is that the union of these intervals, the measure, is the same thing as just summing the individual measures themselves. So the measure of I1 plus the measure of I2 plus the measure of I3 plus the measure of I4. And in this case, the measures of these are basically the length of the interval. So it's B minus A, B minus C, C minus D, B, D minus C, and F minus E. And so it's basically saying that if I take the bigger picture, like this set and this set, and I measure it, that it's the same thing as measuring the individual ones and then adding them all up. So what would this be? This is B minus A plus C minus B plus D minus C plus F minus E, which is the same thing as, so you get cancellations of B, you get cancellations of C, so you get D minus A plus F minus E. And so D minus A is essentially just, D minus A is just the measure of this hypothetical interval that we could have created here. If I created this interval here, that's the measure of that would be D minus A. And so that's accounted for here. And this is just the measure of this interval that's way over there. It's just I want to see if I'm still able to follow the reasoning of the math proof. Oh, you want to see the reasoning? Yeah, yeah. It depends on a lot of, like, the dirty work has already been done. So the idea here is that we start with measurable sets EK, and they're all disjoints. That's what it means to be a measurable partition. And so we first have to establish that the union is measurable. And that comes from result 2.22. So it's a previous theorem that's already been proved, that if you have measurable sets, the union are measurable too. And then what happens here is that we know that E, let's see, how can I say this? We know that the union of sets is less, so the measure of the union of sets is less than or equal to the sum of the individual measures. That's 2.8. So if you want to see it here, that's this right here. So basically, we first had to show that the union is measurable to even work with the union. And then once we have the union, we can start using this property. This property actually doesn't depend on measurability of the union. The union measurability is actually dependent on the second part. But we get this part almost for free because, sorry, that's my girlfriend. We get this part. We get this part almost for free because it's just a definition of outer measure. And so this only depends on a countable collection of sets. So we get this inequality almost immediately. The second part actually does depend on measurability of E. So why does it depend on measurability of E? It's because corollary 2.14.1 requires that the sets be measurable in disjoint. And so we have this is like the first thing that we get from that consequence. Yeah. So the definition for M is actually dependent on M star. It's defined as M star here. Yeah. So everything that we did for M star is applied here. But the only thing different is that we are working with M star under the assumption that we are working with measurable sets. Okay, because M star doesn't only depend on measurable sets. It can be any set. You can use it for any set, but we're restricting to measurable sets. Yeah, the inequalities remain correct here. And so for the first part, we had a set of measurable sets, and we can take a union of that because that's set theory, right? So if we can take the union of that, and so from that we can do the. Oh, actually, no. It is required to show that this is measurable because we are working with M. Yeah, that's true. Yeah. So although doing this is still doable, this is still true. So we could still take the union of these and take its outer measure. This is the M star. This is called the outer measure. And this is equal to this. This is true no matter what. Like even if E is not measurable, even if this is not measurable, this is always true. But because the union of E is measurable, we proved that in the previous theorem. That makes this M star become just M because we're working with measurable sets. And so we get this inequality. Yeah. For for measurable sets, M star is equal. Yeah, we defined it. We just the definition is literally that M is just the same as M star, but we're only working with measurable sets. We're restricting the sets that we're working with to measurable sets, not just a bigger class of sets. Not just any sets, basically. Yeah, M is equal to M star for measurable sets. And so that's the reason why we had to say this. Because if we didn't say this, if this wasn't true, then the most we can say is this is this case. That's the most we can say. But since this is measurable, the union, then we can remove the star from this guy. And since the e's are individually measurable themselves, this is also automatically removable. So we can just write it as m. But at the end of the day, these are the same. These are the same because they're measurable sets. And then corollary, does that make sense? Is that clear, or did I confuse you? So this is automatic. Automatic, no matter what, no matter what. If your set is measurable or not, this is automatic. And because the union is measurable, and we define M to be this outer measure on the restriction of measurable sets, we can just write this as M. And then the second part, that's the first inequality. We had to prove the other direction. That's the rest of the proof, the harder part of the proof. And so to do that, we basically had to bind we had to bind the union in the other direction using partial sums instead. And so the way we leverage that is by using corollary 2.14.1, which I'll show you. So corollary 2.14.1 says if we have a set of disjoint measurable sets, then the outer measure of the union, and it's a finite union. It's just equal to the sum of the individual measures, the outer measures. So again, these have stars, right? So what we got is we got the outer measure of the union of the measurable sets is equal to the sum of the outer measure of the individual sets. But like we just showed earlier, the union of measurable sets is measurable. And each individual set is measurable by the hypothesis. And so the star is removed. And then the way we bound the sum is using containment. So we know that the partial union is contained in the full union. And so by result 2.4, which is the order property of outer measure, we get that this is less than or equal to this. So that's this guy right here. It's one of the first things we proved. So if you have two sets and one's a subset of the other, then the outer measure of A is less than or equal to the outer measure of B. And that should make intuitive sense. Right? If the set is inside another set, it should be smaller in size. So that's basically what we have here. So this set is a smaller set of this set. So the outer measure should be a smaller size. And then again, since unions of measurable sets are measurable, we can get rid of the stars. And we can just talk about the Lebesgue measure. And since this we just established is equal in the previous part, we've established that the partial sum is less than or equal to the measure of the union. So that's here. That's this right here. When I have inequalities like that are like written in that are written like this, and there's like middle terms, but I really just wanted the relationship of the outer terms to be the focus, I rewrite it. And so we have this inequality, and we want to show that the sequence as n of the partial sums as n goes to infinity, we want to show that this is less than or equal to this. That's going to be the end of the proof. And this is where all the undergrad real analysis comes in. And so you have to break it up into two cases. If this is infinite and if this is finite. That's case 1, that's case 2 right here. How do you eliminate inequality? Well, if you're asking how do you get equality, equals is the same thing as less than or equals to and greater than or equal to. Less than or equal to and greater. If you can show this happens at the same time, then you've shown this. And so we've already shown this. Now what we're doing is we're showing this. The whole statement on the page intuitively makes sense. Cool, cool, cool. Nice. Yeah. So all I did was break down. I don't know if you can see on the left side of my notes. I broke down basically this step right here. So right now it's like one line for him. It's one line for Royden, but for an undergrad real analysis student, it's like 1, 2, 3, 4, 5, 6, 7, 8. It's like 8 lines. So you first go through when the bigger guy is infinity, and then that is a kind of like a quote unquote trivial case, because if this thing is less than or equal to infinity, then this guy will either be finite or infinite, and so the inequality should hold. And if it's less than infinity, then you first have to show that the sequence of partial sums converges. So you got to show convergence first. And then from there you can show that whatever it converges to is always going to be less than this guy. And that's what I did here for case 2. Yeah, of course. And this is actually a big theorem. It's a big result in statistics. A lot of this stuff is basically the machinery for probability. So, like, basically, what this is saying is that if you have disjoint events and you take the probability of each one, it's just the probability. I mean, if you take the probability of their union, it's just the probability of each individual event summed to each other. This is kind of like the machinery for that. I bring that up because I know that's a hopefully around the vicinity of data science. It's trying to make it tangible. Okay. All right. That's all I'm gonna work on for measure theory. I'll be back tomorrow for more probably, but I'm gonna switch over to the video game part of my stream. Or actually, let me double check. Yeah, I'll play like a few games. I'm not gonna play for too long. But if you were here for the math portion, Thank you, thank you. If you're here for the math portion, I'm gonna move away from math. But I appreciate you for sticking around. Time to cope. Yeah, and I tried to stream on the weekend, by the way. So if you ever want to like catch my streams, Friday through Sunday is typically around the time I'll stream. Sometimes all 3 of those days. Okay, I'm getting nervous just from logging into my account. Jesus. Thank you, thank you. It, do I call you Omar? Is that crazy stuff? Yeah, it's crazy stuff. Yeah, Omar. Nice having you, Omar. I, f- I s- ay. I have a probably question for you. What do you mean probably? You probably have one or probably don't have one? All right. Yesterday when you DM'd me, I meant to get back to you sooner, but I completely I I got sidetracked. And so I remember like literally when I messaged you. If it's like something more urgent, let me know because that way I can make a note of it. The hint for multiplying the power to t to the homogeneous, it did change. Oh, okay. By the way, Ryan, I keep forgetting to reply to you. The classes are not good. They're very boring. Right now, I'm literally trying to like pass my time by working through basically the stuff that you see on the page on my screen. That's what I'm doing to kind of keep things interesting. Which book do you prefer for mechanics, Morin or Taylor? I think Taylor's a better book for learning mechanics. Morin is it's like a good reference book. It has like a bunch of solved examples. Um, so if you ever get stuck on with like Taylor, like something in Taylor, it's good to use Morin to refer to and see how like some problems are solved. But I think Taylor's a better learning book. My professor mentioned in the problem that the system was frictionless, but in 2C, the professor mentioned no air drag and frictionless surface, so I left in drag. I was not getting a solution that was evolving with time. Interesting. Okay. So there's air drag and friction? What the heck? What's the point of that? I feel like professor would just have you do both if they just want to like make you have a terrible time. But there's really like not a lot of advantage to doing that.